All right, so we're going to do a review of flexural analysis for the midterm, and this will cover over the analysis of beams to determine their adequacy, as well as we'll talk a little bit about the philosophy of design. So our review is going to start with the requirements. The first is rho min, which is equal to 200 divided by f sub y, 0.0033. If rho is less than rho min, then we're not reinforced. We have to have at least the minimum reinforcement, and so this beam is inadequate. The second is we have rho max. The condition for rho max is when the concrete strain is 0.003, the strain in the steel is 0.005. 0.05. What am I doing? So when that is the case, is we're said to be in tension control. And in tension control, the ultimate limit state is the bars will fail. The beam is said to be under reinforced. And we want that limit state because the beam will deflect and crack excessively. And we will notice the beam is cracking and deflecting excessively with enough time to take action. We will say that the structure will tell us that it is failing. So, our analysis method is that rho has to be greater than rho min, and rho must be less than rho max. Now, of course, it can be equal as well. This is 0.0033, and for 4 KSI concrete and 60 KSI steel, rho max is equal to 0.01806. Right? Rho max is an algebraic expression that depends only on the materials from which the beam is made.
So for rho min, we check that in the beginning, and then for rho max, we don't look at that until the end of our equation?
No, we do them both at the beginning, right? Because you're doing analysis. Our first method, before we talked about rho, you would check. You had to assume the steel strain was greater than the yield strain. But we moved on from there. So these are our two checks, and what we'll do is we'll do a flow chart here in a second. If all of this is true, that we're in tension control, what's the opposite of tension control? For in compression control, the beam is over reinforced. How does the beam fail in compression control? Suddenly and without warning by the concrete crushing in the compression zone, which the beam looks the same the moment before it fails as it did when it started to be loaded. So we don't like that. It gives us no warning. It puts people's lives at risk. So we have compression control is sudden failure, sudden brittle failure, as opposed to tension control, which is a slow ductile failure. So, remember we said in our beam, so we've got a beam like this, it has an applied moment due to its loading. It will have reinforcement on the tension face. And up here, we'll have concrete on the compression face. What's the compressive strength? What tensile strength do we assign to concrete? 0, right? And if rho is less than rho max, then we know that the stress in the steel is equal to the yield stress. And so we have a condition in this beam where we have a compressive force in the concrete, we have a tension force in the steel. It's causing a compressive strain in the concrete and a tensile strain in the steel. This is our neutral axis. We don't know what the depth is. C is the depth to the neutral axis. D is the depth to the reinforcing bar. And we make an assumption that the Whitney stress block is acceptable. So our compressive force has a width of the beam B, and A, which is the depth of the Whitney stress block, is equal to beta 1 times C, and beta 1 is equal to 0.85 for F prime C is equal to 4 KSI. It's equal to different values if you have different strengths. Right? If it goes up to 6,000, then it's 0.65. It's a sliding scale, but almost all of our design, very typical to see 4,000 PSI. It's a nice efficient number, and we don't lose as much capacity as our beta 1 falls. The tensile strength, on the other hand, is equal to A sub S F sub Y. So long as the steel is yielding, then the stress in the steel is equal to the yield stress. That's not correct from a pure science point of view, but that is our engineering assumption. It's a conservative assumption. Right? So if we looked at the stress strain behavior of a bar, it would look something like this. This is the strain at yield, this is the stress at yield, and this is the strain at its ultimate behavior, and this is the stress at its ultimate strength. But we don't do that. We assume that it looks like this. And so we have this excess or reserve capacity. This is why the beam moves and keeps cracking, even though we have assumed it's F sub Y. The stress is a little bit, the steel is a little bit stronger as it plastically yields. And this is why we get multiple cracks and large deflections. So we do that for safety. It is an inefficient use of materials. It is cheaper to build compression control beams than it is to build tension control beams. But it's considerably safer. And so, despite what my insurance salesman says, you can't put a price on a human life. So we don't make cheap beams in dangerous buildings. We make expensive beams in safe buildings. Okay, that's our philosophy. If all of this is true, then we can take the sum of the forces in the x direction is equal to 0, right? The first rule of statics, which means that our compression block has to be equal to our tension force, and this is 0.85 F prime C A B has to be equal to AS F sub y, and from there we get A is equal to A sub S F sub y divided by 0.85 F prime C B. B is the width of the beam, A sub S is the area of the steel. We can also take the sum of the moments about the center of the compression block. And that is equal to F, or sorry, the tension force here, right? And it acts at a lever arm of D minus A over 2. We know the tension force is A sub S F sub y, and so our external moment, our nominal moment, is equal to A sub S F sub y D minus A over 2. We need to reduce this by a phi factor. Phi is equal to 0.9 when we have tension control. So our ultimate capacity is phi m sub n is equal to 0.9 A sub S F sub y D minus A over 2. If you were analyzing a beam and it's not in compression control, for our purposes, we say that beam is inadequate. You can continue to analyze. You assign a different phi value. But we will stop and say if rho is greater than rho max, the beam is inadequate. So that was singly reinforced sections. How about doubly reinforced sections? Why do we need doubly reinforced sections? Because sometimes we need additional capacity but the beam size is fixed. So we cannot do anything new. And when we go to do that, we always have our same equation. Our design equation is that the m sub u, which is the applied moment, or the moment you're required to resist, has to be less than or equal to phi m sub n. If it isn't, then you have a failure. So, our doubly reinforced sections, we have reinforcement at the base, and we have reinforcement in the compression zone. Down here, we have a tension force, and that tension force is equal to A sub S F sub y. And up here, we have a compression force, which is equal to 0.85 F prime C A B, plus we have another force acting at a distance d prime from the compression face that is A prime sub S F prime sub S. So we have these two conditions. One is that our beam is going to be singly reinforced, and the second, and doubly reinforced, we're increasing the size of the compression block. And where we increase the size of the compression block, we can increase the amount of reinforcement in the tension face, and thereby we end up with some additional capacity. We have a few things we need to calculate. Rho is equal to A sub S over BD. Rho prime is equal to A prime sub S over BD. If rho minus rho prime is less than or equal to rho max, then the tension steel yields. That is a requirement. We don't design beams where the tension steel doesn't yield. So if rho minus rho prime is greater than rho max, the beam is inadequate. Once we've confirmed that the tension steel is going to yield, we have to ask ourselves a second question. Does the compression steel yield? To do that, we have to calculate our capital K value, which is equal to 0.85 beta 1 F prime C over F sub Y D prime over D multiplied by 87 divided by 87 minus F sub Y. Okay? That's our test statistic. We developed where that came from. And then we check. If rho minus rho prime is greater than or equal to K, then the compression steel yields. If that's true, then our nominal moment capacity is equal to A sub S minus A prime sub S multiplied by F sub Y D minus A over 2 plus A prime sub S F sub Y D minus D prime. And then what do we check? M sub U has to be less than or equal to phi M sub N, where this is the demand, and this is the capacity. And we always want to have more capacity than we have demand for the beam to be acceptable. And phi is equal to 0.9 because we're in tension control, right? We checked rho minus rho prime was in fact smaller than rho max. If, on the other hand, rho minus rho prime is less than K, that means the compression steel does not yield. Which means that we don't know what the stress in the steel in the compression block is. If that is the case, we have to solve a quadratic equation, which is A1C squared plus A2C plus A3 is equal to 0, where A1 is equal to 0.85 beta 1 F prime C B, A2 is equal to A prime sub S multiplied by 87 minus 0.85 F prime C minus A sub S F sub Y, and A3 is equal to minus 87 A prime sub S D prime. We then solve for C using the quadratic equation. And so C,
Go back to that one, please.
there you go. C is equal to minus A2 plus or minus the square root of A2 squared minus 4A1 A3 all divided by 2A1. Right? You'll get two results out of this. One of the results will be positive, one of the results will be negative. Negative distance doesn't exist, only in physics land, so we don't pay attention to negative distance, because that must be some distance that goes into another dimension, or it's particles we can't see, or whatever else you want it to be. So we take the physical quantity C, which remember is the depth to the neutral axis, where the strain is equal to 0. So at that point, we know what C is. We remember that A is equal to beta 1 times C. And that our nominal moment, m sub n, is equal to 0.85 F prime C AB multiplied by d minus a over 2, which is the moment about the center of the compression block. Moment about the center of the tension steel, and plus A prime sub S F prime sub S multiplied by, minus 0.85 F prime C, all of that multiplied by d minus d prime. And what's F sub S, you ask? F prime sub S is equal to 87 multiplied by C minus d prime over C. And then we use our same equation, m sub u has to be less than or equal to phi m sub n, and phi is equal to 0.9 because rho minus rho prime was less than rho max. And you check that way up at the beginning. If we came across a condition where that was not true, we would have stopped very early on in our process and said that doesn't work because rho minus rho prime is greater than rho max, therefore the beam is not in tension control, and beams that are not in tension control are inadequate. Let's take a look at a very quick flow chart for solving these types of problems.
Do we need to go through that whole last part we just did with the quadratic formula if we find K to be conventional steel doesn't yield? I know previously in our examples we just said it's inadequate if it doesn't yield.
If the compression steel doesn't yield, yes, you have to go through the quadratic equation. The only inadequacy is if it's not in tension control. Okay? You start with your beam. Is it single or double reinforced? Single, double. If it's single, rho is equal to AS over BD. Is rho less than rho max? Yes? No. If rho is less than rho max, then you're okay. Phi is equal to 0.9. If no, then the beam is inadequate. If it is okay, we go down, we calculate A is equal to A sub S, F sub Y over 0.85 F prime C B. We had one other check up here, right? So we have rho, is rho greater than rho min? If yes, then we go on. If no, then it's inadequate. If that's A, then we know M sub N is equal to A sub S, F sub Y, D minus A over 2, and that M sub U is phi M sub N. Right? Look how long, see how easy it looks now? Remember when we started? It wasn't so easy. Right? So, doubly reinforced, we check rho is AS over BD. Rho prime is A prime S over BD. Rho minus rho prime has to be less than rho max. If not, it's inadequate. If yes, then we check. K is equal to 0.85 beta 1 F prime C over F sub Y D prime over D 87 divided by 87 minus F sub Y. If rho minus rho prime is greater than or equal to K, or yes. If yes, tension steel yields. Idiot. Compression steel yields. M sub N is equal to A sub S minus A prime sub S, F sub Y, D minus A over 2, plus A prime sub S, F sub Y, D minus D prime. If not, then we need to find C is equal to minus A2 plus or minus the square root of A2 squared minus 4A1 AC all over 2A1. And then R. And then remember that A is equal to beta 1 multiplied by C. And further, that our nominal moment capacity is then equal to 0.85 F prime C AB multiplied by D minus A over 2 plus A prime sub S F prime sub S minus 0.85 F prime C. And we'd want to check the set of brackets I gave you. I think I put the bracket on the wrong side of A prime sub S, multiplied by D minus D prime, where F prime sub S is equal to 87 multiplied by C minus D prime over C. And this is definitely, go back to your notes before and make sure this is A prime sub S multiplied by this whole quantity.
Can you move it up?
Yeah, I'm sorry. Any questions? Yes, sir.
Oh, no, no, there you go.
Good.
In the quadratic formula though, the last A on the top part, that's A3, not AC, right?
Well, A3, yes. Yep. And A1, A2, A3, those are in the notes before. Yes, sir.
Why do we have two different MN equations for the two different cases?
Because one of them is when the steel yields and one of them is when it doesn't yield. And so we need to, we have a different performance or a different result when the compression steel yields versus when it does not.
And then after those two steps, would multiply that by the P-factor for both of them?
Yes.
Okay, and then also on the left, would that be in inches, the MN? Does that come out as inches? That's bad in my notes.
MN would come out as kip inches.
Okay, so do you want that in inches on the
It doesn't matter. You can give it to me in let's see, what's a nice weight that doesn't make any sense? In carats per furlong, or carat furlongs, right? So carat was the weight of diamonds. Furlongs is like some distance that a horse runs. It doesn't matter. But we usually use kip inches when we get these calculations done, and we have kip feet when we've analyzed the beam. Typically we look at our span in beam, so 1 kip foot is equal to 12 kip inches. Yes, that's correct. So if I have 120 kip feet, I have 14,400 kip inches, right? 120 times 12 is going to be 1,440. But you can answer that question yourself if you make sure that you check the units, right? This is area, right? Square inches multiplied by kips per square inch gives me kips. Multiplied by a distance in inches, it's kip inches. Any other questions? I have left you with one. In the I don't think I've told you how to get A, or reviewed, because I have told you before, reviewed how we get A out of our doubly reinforced section. if it, or if the tension steel yields over here, if our tension steel is yielding, then A is equal to A sub S minus A prime sub S, F sub Y over 0.85 F prime CB. And that's for this case where the compression steel yields. If the compression steel doesn't yield, then A is beta 1 times C. And I think that covers everything. So we're going to, I'll post this on Canvas here about noon.